Well, hi, good morning. Thanks so much for joining me here in my shop. It's July 20th, a very hot day here, but again, not hot like other people are experiencing around the world. It's just a regular hot day here. So, yesterday's experience in my shop was interesting. Ended up with smoke coming out of the radio, always an exciting moment. And just cutting off a little extra wire there that shouldn't be there. So in the video, or when I was here, what I saw was some wispy smoke up in this area here. And then I examined all the parts in here fairly carefully following that, and I couldn't really identify exactly where the smoke came from, but I found a pretty whacked out capacitor down here. You probably stopped the video you were watching of me, and you probably rewound it and watched it again. If you didn't see it the first time, you certainly saw it the second time. When I was putting this, putting a video together that you've watched, I realized, oh my gosh, I can watch the video again and see more carefully just where the smoke came out. Didn't cross my mind yesterday in the shop, but afterwards it did. So I know where the smoke came out. So I'm not gonna point to it yet. I'm gonna play that little bit of video from yesterday where smoke and some sparks were happening, and then we're gonna go after that particular part, take it out, examine it, and just ponder the universe while we look at it. So what are we seeing here exactly? Looks like the same frequency. Let me speed this up. See if we can. So there's the actual frequency. That's broadcast. See, the frequency has changed a lot. I'm going to tune the radio and see if this frequency changes here. Yes, it does. So I think what we're looking at is the local oscillator coming back out of the radio where it's developed in the radio and working its way in the wrong direction back to the antenna. And we're seeing it here. So that in itself isn't a problem. What's a problem is that's broadcast band. The local oscillator is pretty strong. What happened to it? Wait a minute, this is working even weirder. Hey, now, did everybody see that and hear that? Briefly, this got a little taller. Oh, wow, that's magic. Can I do that again? No, didn't work again. That got taller, and this thing sounded like a radio for a moment. Oh, there's smoke coming out of the radio. There's smoke coming out of the radio. Son of a gun. Smoke coming out right in here. Son of a gun. Son of a gun. Well, I think we're getting closer to the problem. Well, where did that come from? So I saw wisps of smoke coming up right in here. Okay, now you've watched the flaming video, so we now know it's this capacitor. Is it just the capacitor alone, or has it gotten itself involved with this coil, or we don't know, but my guess is just the capacitor. Yeah, let's see if we can get out of there. So one lead obviously comes here. The other lead is looks like it's coming to this terminal here. Okay, so I'm going to cut this one. I'll leave a bit of wire behind to mark this terminal, but I'm going to go further. Because you know what happens to me while I'm working in here is I leave the shop for 20 minutes at times. On the video it looks like I didn't leave at all, but I left for 20 minutes to go do something in the house, and when I come back I literally can't remember exactly what I was doing. And that would include half cutting out a part. Now let's see. I don't want to damage the capacitor any more than it is already because I want to look at it. Looks like it can just go out the back here. Yeah, no doubt it comes to this terminal. There's 2 wires on the terminal. I only want to cut the one. I can't even see it. Got something. Yeah, that's it. Is it going to come up the backside here? Come out the front. There it comes. Well, it sure looks roughed up. I mean, it's blackened all over the place. Yeah, wax is funny on it. The wax is all really pretty much disappeared in this area. Well, there's still a fair bit of wax here. That's very strange. Probably indicates localized heating. There's blackening here. Let's take a close look with the so-called close-up camera here. Let's see what this looks like. Well, that's easily the most disturbed looking capacitor I've seen. Look at the thing. Oh, it just died right in front of it. The last breath gone. Well, you can really see some carbonite. Oh, look at this. Let me point with a pointer here. Right in there, you can see actual, what looks like carbonized tracking right through here, burning things up, punching holes in it. Wow. Now this was in the radio like this, and this damaged part is pretty much in contact with the coil that it was near. That might be fun to put this on the tester. See what happens. Supply some kind of high voltage to it and see if we get the sparks flying again. Don't think I can get sparks out of my capacitor checker. Well, let's give it a test. It'll be fun. I have the feeling it's going to fail. I'll be pretty sure of that. Fixed my clip yet. Did not turn on when I do. But I turned something. Turned the wrong control. Too excited about this. So what we're going to do with this device is we're going to put a DC voltage. We decide how much on it. Where's the burn part? Right there. We decide how much voltage with this control, and then current leaking through the capacitor, which should be 0 if it's good. Any current leaks through the capacitor will cause this magic eye to close, which I know is hard to see in the camera. But I can report anyway. First thing we're going to do is put 50 volts on it. If it's got a short, we'll know right away. Watch it. I'll watch it. Maybe it's going to spark. No. This is closed. Closed completely. I don't think we're going to get too much further here. Let's put the ohm meter on it. Let's get. Oh, you know what? I can test the resistance with this. I never do. Let's try it. This is an ohm meter too. This device. Okay, so we'll throw this around to. This is R times 100. R scale is the outer scale, so that's 1,000, so that's 100,000. 100,000. We're looking for where the eye opens. Well, it's opening right at the end of the run here, which I don't think is valid. If we disconnect it, we'll get the same thing, yeah. So it's not shorted according to this, but I'm not going to trust that test. I'm going to give it another. If it's not shorted, then we can pound it with more voltage. Maybe we can get, replicate the smoke effect. I can't put this on my keyboard. That'll be the end of the video. Okay. 6 megohms. Open circuit stuff. About 60 megohms. Oh. This says 30 megohms. And if I move my fingers around on it, I'm sure it's gonna, did it just go to 0 there? So the question is, can we make smoke come out of that thing again in some safe fashion? I don't think this is the device to do it, because I think this is probably not able to supply any kind of substantial current at all. Nothing. $250 volts. I'm going to watch the exciting area here. Maybe this will burn up my computer. There we are. No, I don't think anything's going to happen here. We cannot achieve fire. Not this way. Okay, I'm going to stop, have a little bit of coffee, and think about another way to cause a conflagration in my shop here. Okay, so I thought it might be interesting to know exactly where this capacitor is in the radio circuit. So I figured that out. It took quite a while. I'm just going to go through all the steps here. So first we're going to look at the capacitor and see its size. This looks like a 0.01 to me. When you look at this egregious mess here, well, you can really see the burns in it now. Look at that. And the wax is completely gone from here. So there's the word cap, C-A-P, and right below it is the value. It's pretty clear, 0.005, and over here is the voltage rating, 500. DCW. W stands for working, whatever that means. Okay, we'll take a look at the schematic now, and I'll try to show you where I believe that is on the schematic. Okay, now I search this thing high and low. I know one leg of that capacitor is tied to a coil. That's a hint. And I also know its size. It's a big hint, 0.005. So I won't. If I'm running all over this area very carefully, I found only two 0.055s. There's one right here, the C10, and one right here, C29, 0.005, 500 volt. It's one of these two. I couldn't find any other 0.005 capacitor in here. Not that there might not be one. I couldn't find it. So I think it's this one. And the reason is one leg is tied to a coil, like that, and the other leg is tied to a switch. If you come down here and follow these lines on the schematic, it's a big long line here. But in the actual radio, it's direct. The switch connection point is this one here, number 2. That's from the peak down 2, and that matches the position on the switch wafer, and it's the right switch wafer. So I mean, it's all adding up. Oops, it's all adding up. This is the guy. Now, what's he doing here? It's on the plate circuit. So you know he's getting a pretty good voltage here. It could be 250, 300 volts. On startup, it could be quite a bit more for a few seconds. So he's taking the brunt of it. Incidentally, on this schematic, unlike most, I shouldn't say most, other schematics, in this case they've heavied up the B plus line. So everywhere you see the heavy line drawn, B plus is involved. It's going to the plate here. And they don't show it through the coil for some reason. I guess it's pictorially unattractive to do that, so they don't heavy up the coil. But the reason it's on both sides of this capacitor is because it's on both sides of this capacitor. So it's not going through. DC is not going through there. So that's what the heavy lines are. I thought at first it was the signal. You see it come all the way down to the power supply here. 400 volts. Now, that's pretty high. Now, it wouldn't be 400 at the tubes necessarily, but that's a pretty high voltage in this radio. 400 volts. There's no voltage statement here as to what the voltage is on this line, except that 400. That's a rating, isn't it? That's a rating, I think. That's probably a rating for the capacitor, so we could guess 300 volts here. Probably a good guess. So the guy's got 300 volts on him. And what's it doing? I'd have to get my book out and read this to be absolutely sure. It's right on the plate circuit. Probably has something to do with oscillations, unwanted oscillations, or something like that. I'm not entirely sure. That's it. Not a tiny capacitor. It's not a big one either. Don't know. For sure, if it's shorted out, which it was doing, it's got B plus and this power supply behind it to push current through it and cause sparking at the high voltage. So there's no question that. And could this quiet the radio? Now this is an interesting question. Oh yes, absolutely. If this were to short right out, there's bad things that could happen. It could burn out this coil, burn out this coil. This is a bad guy to have a full short. But you saw when I tried to measure the resistance, it wasn't a full short. It continually, I guess, burned the short clear, probably repeatedly. So why would AM work and FM not? And I have no answer for that. FM, there's no FM. That's why the FM didn't work. Shortwave. Why would the AM work and the shortwave not? Got no answer for that one. Something to do with the switch here. I don't know. In some of these radios, the AM signal will bypass the RF amplifier and go straight to the mixer. So I looked for that here. It's tricky to figure out. The AM antenna signal's here in this coil, coming down on this wire, going into the switch. The switch is set to AM right now on the picture, so we can see it coming out on this wire, coming over here, meeting up with the tuning capacitors. Must be another way out of here. Oh, this one. So it goes up here, up on this line, and then it goes just through the capacitor, get to the grid of the first tube. So you can see the AM signal gets to the grid of the RF. It doesn't bypass it, like I'm saying. In some radios, the output of this transformer goes straight over here and bypass all this stuff. And then here's the AM coil here too. AM coil. Well, let's not jump to conclusions here. Did this burn out? Did this one burn out and this one not? If this one burns out, there can be no B plus on the tube here. And I don't think the AM signal would come through it. But we can conjecture all day. What I need to do is put a new capacitor into this position and then operate the radio and just see if it's come back to life or not. I also, because this capacitor is laid up right on top of this coil, the sparking may have damaged this coil, although I don't think so. How would I know? You know, maybe the best way is just to replace the capacitor, fire up the radio and see if it works. Go from there. Okay, that's my plan. Replace the capacitor. I better not use the term fire up the radio. I'm trying to avoid firing it up. And we'll see if it's improved things or not. Got to be some kind of improvement coming. Okay, time to find out what difference this has made to the radio. I have to guess. Big difference. Volume's down. Switch is on, plug is in, and I've got the antenna connected. The antenna is switched on, and we're going to start on broadcast band. we go. Can bulbs behaving correctly? Now that capacitor is right on a B plus line, so making a mistake with it, not a good thing, but I'm pretty sure I didn't make a mistake. Volume up. Fingers are crossed. There it goes. Okay, we're operating on a low voltage here, 85 volts. Good. Okay. No particular smoke coming from anywhere, just a cat crying behind me. Let's go full voltage here. Peanut, you can't go in there. He wants to go in our spare bedroom, but what's that? Ooh, what's that sound? That's not a good sound. Ooh, I like that sound. Okay, well, quickly, before we get something else on fire here, how about a shortwave band? How about a shortwave band? Still dead. Still sounds dead. That's disappointing. Strong station around 9.3. Not a thing. Full volume, tone up. Not a thing. Oh, you know why? I've got to deal with my cat. I know why it's not working. I'll fix it in a sec. Okay. Out, he says. Okay, I conned my cat into going into the garage. The sad thing here today is one of our cats is missing. Didn't come home last night and still isn't home. That's the black one. It's very, very upsetting. So while I've been working on this radio, I've been running around the neighborhood looking for her too. Not showing up. Let's try another band. That's a little better. Still full volume. Tuning. Ooh. Ooh, that's a weird sound, eh? Oscillation in the radio. So it sounds like. So again, a strong station 9.3, it's actually right off the band here. But that sounds like a radio, doesn't it? Oh, I didn't fix it in. Okay, right. It didn't. Okay, let's do this. I'll detach the antenna from the ground and I'll stick it on the antenna terminal. How about that? Then we'll go back one and we'll try again.
One day, a conversation with Dawson's teacher gave the family a ray of hope. The teacher knew of a...
So that's going to be 9.3 there. Okay, next band. Oh, that's lovely. Look at that. 9.3 is off the scale, I think. Surprisingly quiet. Next band. Next band is this one. 11. Sounds the same. Really would expect to pick stuff up here. Last band. 15 megahertz. Well, we're way ahead of where we were, that's for sure. Now, didn't I find that this capacitor back here was nulling out the antenna a bit? Let me bypass it. Just go on this wire here. It's definitely more antenna signal. pick anything up. Let's go back down through them. Oh, this one's quiet. One with the burned out light. There's nothing there. Back up. Nothing. Oh, I'm turning the knob the wrong way, so I've turned it to phono. Pick one. Just leaving the volume. Just listen to the hiss level. Why so quiet? That's a good question. Why so quiet? Why so quiet on the one band? Well, piles of bad capacitors still in here. Okay, so that did solve a big problem, I think, but it didn't solve all the problems. And again, we probably have kind of general degradation in here because look at all the wax capacitors. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Any hidden down to 12. There's a dozen of them in here. They all got to go. Probably because of the lack of performance in the front end of the radio. Maybe a good place to start is the front end of the radio and start changing out capacitors there before going too much further. Typically I start with the audio and kind of work my way back through the radio to the front, knowing that the sound is working good. Well, there's lots of sound coming out of it right now, so we can assume the audio circuits are okay. And just focus on these radio circuits. So it would be capacitors that are tied in with these coils and stuff, all the stuff up in this area here. We change all these out and then do another performance check. And I may want to take a moment and all these ones are later on in the radio. But this is all the RF stuff up here. And you know, the curious thing now, unless I'm mistaken, and I may be mistaken because I looked at the schematic earlier, but maybe I'm mistaken. That capacitor is in some way connected to these twisted wires. Isn't that interesting? I don't know if that's really true. I think it's the, you know what, it's not. It's the other 0.005 capacitor, which is probably ready to let go too. It's also got B plus across it. I wonder which one that is. Okay. Okay, I'm so disturbed about our cat here. I'm having a hard time thinking about this. Okay, let me just see how far into this. Maybe, yeah. What? Yeah, I'm confused. What? Okay, I think we're at about the half-hour mark on the video that I'm preparing for this. So there's some more time. Why don't we go another step? I think what I'd like to find out is, or what appears to me to be the case from a couple observations, is the local oscillator is very weak on the C band. The C band is the shortwave band that covers a big range of frequencies. The other three cover a very small range of frequencies spread out on the dial for convenience in tuning. So on the C band, you're turning the tuning knob like this to tune stuff in, but on the other bands, which are band spread, you can be doing this. It's much easier to tune in on the band spread bands, but the C band is the one that appears low. So if the local oscillator is weak, there's two ways I know of to detect that, aside from hearing the radio not working. One is to measure the grid voltage on the oscillator grid of the mixer tube. That voltage should be negative, and the stronger the oscillator, the more negative it is. So I could potentially hook up my meter here, turn on a working band like the broadcast band, see a value. The value itself doesn't matter, but see a value over here, and then flip through the bands and see if that value stays about the same or if it drops off on the bad band. The bad band. I left the power onto this radio. Shame on me. And let's just get this out of the way here. I don't like having extraneous test leads and stuff around on my bench on account of when the smoke flies. which apparently can really happen. You don't want a bench full of stuff. You got to try to think fast and act fast. So it's grid 3 on the mixer tube. Now the radio's not switched on, even though it's plugged in and the power's on. So pin, it's grid 1, and I don't know what pin it is offhand. So it's a 6SA7, 6SA7. And we'll find grid 1 is pin 5. Yeah, grid 1. So there's 2 signal grids, if you like. Grid 1 and grid 3 on this kind of tube. The antenna is hooked up to 3, and the local oscillator is hooked up to 1. And the 2 of them are operating the tube together, and that's where the mixing goes on. And you get the sum and the difference of the 2 frequencies that are in there, mixing it up. There isn't 2 frequencies, by the way. The entire antenna signal is being converted to a different frequency. So it's not that you're tuning a particular frequency, like let's say 1010 AM, and then it goes through this tube and gets converted to 455. That's not quite what's going on. What's really going on is the entire range of frequencies on the antenna, to a fair degree. Okay, there is a bit of a response curve involved here, but pretty much the entire antenna signal is getting converted down to around the 455. That's no, down would be this way. And so now the whole range of tuning frequencies is down here around 455. One of them may be right on 455, and that's the one that keeps going through the radio. But they're all there. They're all getting converted. Yeah, there is some tuning in the front end, but it's not that sharp. Okay. Right. So I want to get on right. What happened to me? 5. 5 is the number. Oh my gosh, I almost forgot that. So we'll look for 5 up here. Again, the radio's not on. I'm looking for the key on the. Where are you, Mr. Key? It must be hidden. There it is. Okay, I think I see it. Okay, if I really saw it, I would make pin 1 2, 3, 4, 5. I'm not sure. Resistor right there. It's going way over to this other tube. That's not good. I don't think I got the pin right. Okay, let's pull the tube out. There's too many wires here to see where the key is clearly. Okay, the key is where I thought it was. And then, so that's 1, 2, 3, 4, 5. Interestingly enough, pin 5 has this gimmick capacitor on it. And I'm going to take a look on the... let's put the tube in. Take a look at the schematic and just see if that agrees. In that case, we have a capacitor coming up this way, and I think that makes a lot more sense. Coming over to the switch here. Is this on the gimmick capacitor on the grid, on grid number 1? Okay, let's go and check it out here. So we're looking at a 6SA converter tube, and so here's the twisted capacitor, and one leg, well my gosh, one leg comes up to what is grid number 3, which is the signal grid, which is the signal coming through here from the antenna, and the other leg is hooked up to the other signal grid. So the answer is yes, the twisted capacitor here is connected to, well, it's connected to both signal grids. So I just get on this terminal, measure the voltage, go through the bands, and see what happens. Okay, so once again, I'm going to use a clip lead here, so I don't have to try holding this voltmeter in there. Now you got to think, if a little twisted pair of wires is having an effect on this circuit, good grief, hooking up this great big wire and this meter, there's a good chance that's going to have an effect too. But it's all relative. So I guess if it weaken the local oscillator on every band, and the one that's bad will be even just that much, well, I think it's dead actually, but let's see. So we have the meter connected. We have the radio ready to go. I put them on the dim bulbs here always, and here we go. And we should flip this on to broadcast and turn up the volume a little bit. Okay, dim bulbs behaving correctly. So we're not afraid, not afraid. And we're watching this guy. Now, oh my gosh, what was that? What was that sound? So here we are, negative voltage. This is on the negative setting, so upscale reading is actually negative. That's what we expect on a grid. I don't need to listen to that. And it is about, this is the 15 volt scale, so it's around 7 volts. We're on the broadcast band. I'll tune the radio. Ever wonder why your radio's louder at one end than the other? Yikes, what was that? You can see the local oscillator strength is going up and down here a little bit, but the radio goes quiet way at the top here. Probably just alignment. Now, what we're going to do is we're going to snap through the bands. We're going to watch this and see what it does. Here's the big test. The first one coming is the C band, 6 volts. Next one, 9 volts. Next one, 6 volts. Next one, way down to nothing. Oh, well, this is a complete, and that's phono. This is just completely different from what I expected. Now, it's quite possible the connection here is what's causing the problem. The way I've hooked up my meter is causing the radio to misperform. So, I mean, this is hopeless. Six volts on the 11 megahertz band, 9 volts on the band we listened to. Did we tune something in there? And this is the band that's quiet, 6 volts. It's not nothing. Instead, 15 megahertz band is nothing. Oh my gosh, really? Okay, is the test bogus? Now, I have another way of checking the strength of the local oscillator we're going to take a look at. So first I'm going to depower this. I can stick my fingers in here and pull this off. Okay, put it back on. Now I have a SDR radio receiver in here. It's actually sitting right here. It's a cheap little $40 radio. I think they're worth, I think they cost $60 now. Hello, inflation. So the thing about this little radio, it's just a little box here, is it's SDR, software defined radio. So it actually works with a computer. No computer, no radio. You must run software to operate one of these radios. So I'm going to put that software on the screen and we're going to take a look at it, and then we're going to use it to receive the local oscillator signal, which undoubtedly is broadcasting a little bit out of the radio and just around in my shop here. We should be able to pick it up on this radio just using basically an antenna close to the radio. That's basically what it amounts to. So let me get all that happening here. Okay, so you're looking at a display from that little radio, the SDR radio, and what it's showing here, these lines down here at the bottom, well, one of them is my cursor, obviously. The other lines are signals that the SDR is picking up here in my shop. The color varies with the strength. The strongest one is this yellow one right here. Now, is that the local oscillator? all I have to do is tune the radio a bit. If that's the local oscillator, its frequency will change. So just watch and see what moves. I'm just going to tune the radio a bit. And there you go. So what I'm going to do now is I'm going to tune the radio to a specific frequency on the dial. I'm going to pick 1 million because it's really easy. So that's tuned to 1 million. The local oscillator should be 1455. So where'd it go? Here it is here. So if we just click on it, did I miss a bit? There. So now I've tuned the SDR to the local oscillators. Hear those clicks coming out of the radio? Isn't that scary stuff, eh? Something else is going to bite the dust. It's definitely there. I'm just checking to make sure I'm following the local oscillator. Okay, so the local oscillator is running at 1470, and the radio dial is pointing on exactly 1 megahertz. So that's an indication that the alignment is out a little bit, because what we should find is the local oscillator should really be where the red line is. It's just a little bit out. Okay, that's enough of that. Now we sort of have a kind of a standard base to work from. The strength of the local oscillator here, let me move the red line. The strength of the local oscillator is shown by the color. Here's the color range over here. So we can see if it just gets weaker on other bands. And I didn't even show you how I'm picking this up. Let's go with the test, and then I'll show you exactly how I set the SDR antenna. It's no big deal. So we're leaving the broadcast band. First we're going to another band. So you see the local oscillator has just come to an end here because it's running at a different frequency. Now the radio is tuned into, I'm going to tune in to 10 megahertz again for easy calculation. What's 10 megahertz plus 455? That would be 10,455. So we will work our way up there to 10,455. We'll put the red line where it should be. We should be finding a local oscillator where the red line is. It should be a nice yellow. There's a red thing over here. Okay, so I'm going to tune the radio slightly and we'll see if anything moves. Sure enough, there's the local oscillator. So again, alignment is out. That can really affect the performance of the radio. It's quite a ways out here. But the oscillator is there. And it's producing a red line. Okay, so I mean, this is not a very quantitative test here. So we'll go to the next band. The next band up 9. So the local oscillator hasn't changed very much. Let me tune the radio to 9.5. Now we got to add 455. So just go just below it a little bit. That should put the local oscillator at 10 megahertz. Should be at 10. It's just off the scale. I'm going to move my scale over. Do we see anything pretty strong? Look at that. Big strong thing here right near 10. Again, tune the radio slightly to make sure that's the local oscillator. It's super strong here. Oh, it's not. What's happening here? Everything under the sun is moving. So these radios, because of the mixer tube, do a lot of weird things. And when I use the SDR here, which gives you an ability to kind of see the spectrum, that's was normally never done before, because nobody had all this kind of equipment that exists today. So back in the day, nobody could really understand this stuff. I don't think. Certainly not by. So the two lines way on the left, these two, they're moving in the wrong direction. Let me force this one onto 10 there. Can I do that? Can I get it there? The radio's gone quiet. So now we have 10 megahertz. So if you subtract away, now subtract or add 455. You know, the local oscillator could be on the other side. So that may not make much sense what I'm saying here as I mutter to myself, but so be it. If the local oscillator is below, and we have the radio tuned to, let me put it back on something simple here, 9.5 is the simplest thing I can do. Tuned to 9.5, then the local oscillator would be around 9 megahertz. Be a rate around 9, right around here. Okay, so let's keep our eye around here. I'm going to tune the radio a bit. I'm going to tune it up, so the oscillator should go up. A lot of things going down in frequency. Isn't that weird? All that weird stuff in there. The only conclusion I can come to is that thing up around 10 is the actual local oscillator. The local oscillator is running above the target frequency. That's how they've set this up. And it's out. Because with that at 10 megahertz, the radio dial should be pointing at 9. Oh, it's pretty close on the dial. 9.55, wouldn't it be? Okay. We're going to go on to the next one. So this one, our local oscillator seems fine. Next one. Okay, now we're at 11 megahertz, and on the dial, doggone it, there's nothing really simple here mathematically, so I'll pick 11.75 arithmetically, and we'll jump up to 11. Here's the shortwave band. You see on this radio they highlight the shortwave broadcast bands by coloring them a little bit. Okay, tune the radio. We got the local oscillator in view already. Looks like it. Which one of those is the local oscillator? So if you look at these two lines, when I'm tuning the radio and they're moving around, you'll see that this one moves at twice the rate of this one. So for every, 5 kilohertz I move this one will move 10. Watch this again. It sure looks like that anyway. I really think that means this is the local oscillator. If this is the local oscillator, the radio is currently tuned to a frequency 455 kilohertz below that. What happens if you subtract 455 from 175? Yeah, I can't do it. Yeah, okay, I'm getting my calculator out. I'm too stupid to do this. 12,175 minus 455 equals 11,720. So I'm looking on the dial now, and it's tuned to 11,750, a little ways away. Again, the local oscillator seems to be there, seems to be strong. Next band. Okay, so this is the 15 megahertz band. This is the one we saw virtually no voltage developing on the grid. So 15 megahertz here. We're not really making our discoveries in the way I would have hoped. But, this can lead to an elimination of a potential problem. The problem being a weak local oscillator. Okay, I'm going to vary the tuning. There it is. It's red. Now I'll check to see if it's anywhere near the right frequency. In this case, I can tune this radio almost to 15 megahertz. So we're close to 15 megahertz here. So we should be close to 15,455. So there it is at 15,500, and it should really be 455. Should be over here, where this line is. So again, alignment is out. But the local oscillator is there. It's right there. And it's red, which means it's a fair strength. What do we find out? We found out the oscillator is oscillating. Let me go to the top of this band. This is the stress test on the radio. Actually, this isn't the stress test. Still there. Yep. Still there just fine. More clicking and popping. Earlier on, when I was working on the radio and it was clicking and popping, and I noticed the dim bulb lights, which were on at the time, were also going up and down, and that was almost certainly that capacitor drawing extra current out of the radio power supply. Let me show you how I'm doing this antenna here. Nothing fancy whatsoever. So this is the lead going to the SDR radio over here. This is the antenna lead, if you like. It's not even connected, right? And the ground, I just clipped it to the chassis for no really good reason. You don't even need to do that. Sometimes I just lay this wire on the bench over yonder and it can pick up the local oscillator because they're generally quite strong. Okay, so we've eliminated the local oscillator as being any kind of performance causing problem, but we've identified alignment as being way out on this radio. Well, out. I shouldn't say way out. I should just say out. Out. Needs attention. Okay, so the name of the game from here forward is we're just getting back to changing out capacitors, and we'll change them out up here and just check the radio periodically as we're doing this. Ultimately see what happens. But that's the end of today's efforts here. So thanks a lot for watching. And see you on the next video. See ya.